Venus is one of the brightest objects in the night sky. From Earth, it can appear before sunrise or linger after sunset, shining with a pale steadiness above the horizon. No surface features are visible. No continents, valleys, or mountains announce themselves through the light. Even through a powerful telescope, the planet offers almost nothing but a smooth, luminous disk. What you are seeing is not the ground. You are seeing clouds. They wrap around the entire planet, forming a global veil so complete that visible light cannot reach the surface and return to space for centuries. This brightness encouraged imagination. Beneath those clouds, some observers once pictured warm oceans, tropical landscapes, or a younger version of Earth. The real planet was hidden too well for those ideas to be tested. Venus is nearly the same size as Earth. Its gravity is familiar. Its rocky body formed from much of the same early material as our own world. Yet above its surface rests an atmosphere unlike anything a human being has ever experienced. Most of it is carbon dioxide. Near the ground, that atmosphere presses down with more than 90 times the pressure found at sea level on Earth. The surface temperature remains close to 870 degrees Fahrenheit, hot enough to damage or destroy most machines within a short time. Higher above, the air cools. Pressure falls. The clouds thicken into broad layers of sulfuric acid droplets, carried by winds that race around the planet far faster than the solid world turns beneath them. From a distance, the result looks calm. The cloud tops reflect so much sunlight that Venus becomes brighter in our sky than any star. Their pale surfaces reveal little of the motion within them. Beneath that smooth appearance, currents rise and sink. Waves pass through the atmosphere. Chemical reactions unfold in sunlight. Winds circle the planet in only a few Earth days, while the rocky globe below requires about 243 Earth days to complete one rotation. The clouds and the ground seem to belong to different clocks. To understand Venus, it is not enough to look at its surface from above. The atmosphere itself is the story. It is a deep, moving environment, extending from tenuous upper layers exposed to sunlight down through acid clouds, warmer haze, dense carbon dioxide, and finally the heated air resting over volcanic plains. Each level changes the meaning of the planet. At one altitude, temperatures and pressures can resemble conditions near Earth's surfaces, though the chemistry remains hostile. Farther down, droplets begin to evaporate before they can reach the ground. Deeper still, the atmosphere becomes so dense that it behaves less like ordinary air and more like a heavy fluid pressing against every exposed surface. The descent is gradual. There is no single boundary where the familiar becomes alien. Light fades by degrees, pressure builds, heat gathers. The sky changes color. The motion of the winds shifts as the clouds give way to the lower atmosphere. Tonight, the journey begins above those clouds, where Venus is still a bright world suspended in sunlight. From there, we will move downward, layer by layer, through an atmosphere that has concealed an entire planet while preserving the history of how that planet changed. The veil is not empty. It is the record. Seen from space, Venus appears almost featureless. Its cloud tops form a bright globe with only faint streaks and subtle variations in tone. Invisible light. There are no familiar landmarks to follow. The atmosphere reflects most of the sunlight that reaches it, turning the planet into a smooth white presence against space. But the clouds are not motionless. They are carried around Venus by winds that move far faster than the surface below. Near the cloud tops, the atmosphere can circle the planet in roughly 4 Earth days. The solid world beneath takes about 243 Earth days to rotate once. This difference is called superrotation. The atmosphere does not simply keep pace with the ground. It races ahead of it, flowing westward around the planet at speeds that can exceed 200 miles per hour near the upper clouds. From far away, the motion is difficult to see. The clouds appear too uniform in ordinary light. Yet when astronomers observe Venus in ultraviolet wavelengths, hidden patterns emerge. Dark bands cross the planet. Bright regions bend into broad curves. Long streaks stretch across thousands of miles. These markings are created by differences in how the clouds absorb ultraviolet sunlight. Some of the absorbing material has been identified, but not all of it. Sulfur compounds and other molecules may contribute. One part of the pattern still comes from an absorber whose exact identity remains uncertain. The result is a moving map written in chemistry and light. By tracking these features from one image to the next, scientists can measure the winds. The markings shift across the disk, revealing how quickly the atmosphere turns and how its speed changes with latitude. Near the equator, the flow is especially strong. Toward the poles, the circulation becomes more complex. Clouds rise in some regions and descend in others. Waves travel through the atmosphere, carrying energy between layers. The entire system behaves like a planet-sized engine. Sunlight warms the cloud tops unevenly. The equatorial regions receive more energy than the poles. Dayside is heated while the night side cools. Yet Venus rotates so slowly that its day-night pattern is unlike Earth's, and the atmosphere responds by redistributing heat around the globe. The thick carbon dioxide air is remarkably effective at doing this. Even though the surface experiences long periods of daylight and night, temperatures near the ground vary very little between the two hemispheres. The atmosphere stores and transports heat so efficiently that the night side remains almost as hot as the day side. Higher above, the contrast becomes more noticeable. At the cloud tops, sunlight can shape local temperatures more directly. Winds carry warm air toward the night side and return cooler air toward the illuminated hemisphere. This motion interacts with the larger, super-rotating flow. The causes of super-rotation are still being studied. No single explanation has fully settled the question. Atmospheric tides generated by solar heating appear to play an important role. Large-scale waves may transfer angular momentum through the atmosphere. Turbulence, vertical circulation, and the interaction between different cloud layers may also help maintain the rapid winds. What seems certain is that the motion is not accidental. The atmosphere continuously exchanges energy and momentum across enormous distances. Waves rise from deeper layers. Solar heating creates repeating patterns. The clouds respond as one connected system, even when different altitudes move at different speeds. Some of these motions form structures that span much of the planet. Spacecraft have observed immense atmospheric waves above the cloud deck. One especially large feature has appeared near the equator, stretching for thousands of miles and seeming to remain nearly fixed relative to the surface, while the surrounding clouds rush past. Researchers have linked this type of pattern to the landscape below. Venus has mountains, highlands, broad volcanic plains, and long ridges. When dense lower air moves across elevated terrain, it can generate gravity waves. These are not waves in gravity itself. They are oscillations created when displaced air is pulled back toward its original level. On Earth, similar waves form when wind crosses mountain ranges. On Venus, they can travel upward through the atmosphere. By the time they reach the cloud tops, they may leave a visible signature far above the terrain that produced them. This creates an unusual connection. The surface is hidden by clouds, yet the mountains may still announce their presence through the motion of the atmosphere. The solid planet affects the air. The air carries that influence upward. Orbiting spacecraft then detect the pattern from space. The landscape becomes visible without ever being seen directly. Venus also has polar vortices. Near both poles, the atmosphere turns into rotating structures with shapes that can change over time. Some observations have revealed double-lobed patterns, almost like two connected eyes within the circulation. These vortices are not stable objects with permanent outlines. They stretch, twist, and reorganize. Their forms may shift over hours or days as winds at different altitudes interact. Warm air descends near the poles, while surrounding currents feed the rotating system. The South Polar Vortex has been observed in infrared light, allowing scientists to study temperature differences within the clouds. The pattern can appear symmetrical during one observation and distorted during another. Its motion reminds us that Venusian weather is not frozen beneath a uniform cover. It is active, it is layered, and it is not always predictable. The upper atmosphere also changes over longer periods. Wind speeds measured during one mission or decade do not always match those measured later. Some observations suggest that the cloud top circulation can strengthen or weaken over time. The reasons remain uncertain. Small changes in solar heating may contribute. Interactions between atmospheric waves may alter the flow. Deeper layers may transfer momentum upward in ways that are difficult to observe directly. Because the atmosphere is so thick, events far below the visible clouds can influence what happens near the top. Yet the path between those layers is not easy to trace. This is one of the central difficulties of studying Venus. Scientists can observe the upper clouds from orbit. They can measure winds by following ultraviolet markings. They can detect thermal patterns in infrared light. But the atmosphere between the cloud tops and the surface remains only partly sampled. A few descending probes have passed through it. Balloons have floated within it for brief periods. Landers have transmitted from below. Each has offered only a narrow passage through a system that is always moving. Still, those passages have changed the way the planet is understood. They showed that the bright veil is divided into distinct layers. They revealed that wind speed changes with depth. They measured rising pressure, changing temperature, and shifts in chemical composition. They also confirmed that the rapid motion above does not continue unchanged all the way to the ground. Near the surface, the winds become much weaker. The dense air moves slowly there, often at only a few miles per hour. But because the atmosphere is so heavy, even a modest breeze can exert significant force. The difference between the racing cloud tops and the slower lower air creates vertical shear across the atmosphere. Venus is therefore not wrapped in one wind. It is enclosed within many. Each altitude carries its own rhythm. The upper clouds circle quickly under direct sunlight. The middle clouds move through dimmer regions. The lower atmosphere settles into denser, hotter motion closer to the ground. From Earth, all of this remains folded into a single bright point near the horizon. A planet that seems steady is turning beneath winds that refuse to follow it. The first true cloud layer begins high above the surface. At these altitudes, Venus no longer resembles the furnace hidden below. The air is cooler, the pressure is lower. Sunlight still reaches through the upper haze, though much of it is reflected back into space before it can descend very far. The clouds extend across tens of miles of atmosphere. They are not made of water. Their droplets consist mainly of sulfuric acid, mixed with a smaller amount of water, suspended within carbon dioxide air. Each droplet is tiny. Most are far smaller than a grain of sand, and many are comparable in size to particles found in terrestrial haze. Together, they create one of the most reflective planetary coverings in the solar system. Sunlight enters the cloud tops and encounters layer after layer of droplets. Some light is absorbed, much of it is scattered. Photons change direction repeatedly before escaping back towards space, producing the pale brightness seen from Earth. The same clouds that conceal Venus also make it easy to find. Their existence depends on a chain of chemical reactions unfolding above them. Sulfur dioxide rises from deeper in the atmosphere. Some of it may originate from volcanic material released at the surface, though the present rate and pattern of volcanic activity remain active areas of research. Once sulfur dioxide reaches higher altitudes, ultraviolet sunlight helps drive reactions that transform it into other sulfur-bearing compounds. Through several chemical steps, sulfuric acid forms. The acid condenses around small airborne particles. Droplets grow, collide, divide, and settle. Some are lifted again by rising currents. Others sink toward warmer levels, where they begin to evaporate. This means the clouds are not permanent objects. They are a continuing process. Material moves upward. Chemistry reshapes it. Droplets appear. Gravity carries them downward. Heat removes them before they reach the ground. A sulfur cycle turns through the atmosphere, though many details remain unresolved. The exact pathways linking the lower atmosphere, the cloud deck, and the upper haze are difficult to observe across an entire planet. Measurements have been separated by years, missions, instruments, and narrow windows of descent. Even so, the broad structure is clear. The upper clouds contain smaller particles and receive the strongest sunlight. Beneath them lies a middle region with a different balance of droplet sizes. Farther down, larger particles become more common before rising temperatures begin to thin the cloud material. Researchers often divide these particles into several size groups. The smallest form a fine haze. Medium droplets provide much of the visible cloud mass. Larger particles appear in the deeper layers, though their exact composition and internal structure are less certain. A droplet can begin high above Venus as a trace amount of vapor collecting around a microscopic seed. It may remain suspended for some time, carried sideways by winds and vertically by atmospheric motion. It may join with other droplets or absorb more material. As it descends, the environment changes, pressure increases, temperature rises. The balance between liquid and vapor shifts. Eventually, sulfuric acid begins to evaporate. The droplet becomes smaller, then disappears into the surrounding gas. Its material may later rise and become part of another cloud. There is no ordinary rainfall reaching the surface. Drops may form and fall within the clouds, but the lower atmosphere is too hot for them to survive the journey. Long before reaching the ground, they return to vapor. On Earth, rain can connect clouds directly with oceans, soil, rivers, and living systems. On Venus, the falling liquid never completes that descent. It belongs to an atmospheric loop suspended far above the landscape. The cloud deck is often divided into upper, middle, and lower regions, but the boundaries are not sharp. There are transitions rather than walls. Near the top, around 40 miles above the surface, pressure and temperature enter a range that can appear surprisingly familiar. In parts of this region, the pressure resembles conditions found near sea level on Earth. Temperatures may also fall within a range that liquid water could tolerate under other circumstances. This similarity has sometimes encouraged comparisons with Earth, but pressure and temperature are only two parts of an environment. The surrounding air is dominated by carbon dioxide. The droplets are strongly acidic. Water is scarce. Ultraviolet radiation reaches the upper layers. Winds move with great speed, and the chemistry follows pathways unlike those in Earth's atmosphere. A familiar temperature does not make a familiar world. Still, this region remains scientifically important because it shows how dramatically conditions can change with altitude. A planet whose surface is hot enough to melt lead possesses cloud layers where the thermal environment is far less severe. Across a vertical distance of only a few dozen miles, Venus passes through conditions that resemble several different worlds. The top, the atmosphere, fades toward space. Within the clouds, acid droplets move through temperate air. Below them, pressure and heat begin their long rise. This layered structure has influenced the design of exploratory missions. A balloon placed within the middle clouds would not face the same crushing pressure as a lander on the ground. It could move with the winds, sampling the atmosphere across a broad distance rather than following a single vertical path. 2 Soviet Vega missions tested this idea in the 1980s. Each released a balloon into the Venusian atmosphere. The balloons floated within the cloud region for almost 2 Earth days, carried thousands of miles by the planet's circulation. Their instruments measured temperature, pressure, wind, and variations in the motion of the surrounding air. They did not remain in one place, they became part of the weather. As the balloons crossed the night side, they rose and fell slightly within the atmosphere. Their movements revealed vertical currents and turbulence hidden inside the broad westward flow. For a brief interval, human instruments traveled within the clouds rather than observing them from outside. The environment around those balloons would have appeared unlike the bright white globe seen from space. Inside the cloud deck, visibility would have been limited. Light would have arrived from many directions after scattering through countless droplets. The sun itself might have appeared as a diffuse bright region rather than a sharp disk. The sky would not have been blue. Earth's blue eye comes mainly from sunlight scattering through nitrogen and oxygen molecules. Venus has a different atmospheric composition, a much greater depth of air, and cloud particles that reshape the light before it travels far. Within and below the clouds, the illumination becomes muted and amber-toned. Farther down, sunlight weakens until the surface receives only a fraction of the brightness found above. Yet the ground is not in complete night during the Venusian day. Diffuse light filters through, spread across the sky by repeated scattering. A person could not stand there to see it, but a camera built to survive long enough might record a dim, orange landscape without a clearly visible sun. The clouds also contain markings that are still not fully understood. Ultraviolet images reveal dark patches where an unknown substance absorbs part of the incoming solar radiation. Several candidates have been proposed, including sulfur-bearing molecules, iron compounds, and combinations of particles shaped by photochemical reactions. No single explanation has yet accounted for every observation. The absorber matters because it influences how much solar energy the upper atmosphere receives. Darker regions take in more ultraviolet light. Brighter regions reflect more of it. These differences may affect temperatures, winds, and cloud circulation. A chemical mystery is therefore connected to the movement of the entire atmosphere. The dark markings change shape as they travel. They stretch into bands, gather into broad patches, and break apart beneath atmospheric shear. Their lifetimes vary. Some persist long enough to be tracked across much of the planet. Others fade before completing the journey. The cloud particles themselves also vary by location. Near the equator, strong sunlight and rising motion can produce one pattern of haze and droplets. At higher latitudes, descending air and polar circulation create another. The clouds may thicken, thin, brighten, or darken according to chemistry and motion acting together. There is no single sample that represents the whole planet. A probe descending at one latitude passes through one local atmosphere at one moment. Another probe, released years later elsewhere, may measure different particle concentrations or chemical ratios. This is one reason Venus continues to resist simple description. Its clouds are global, but they are not uniform. They form a complete covering. Yet that covering changes by altitude, latitude, local time, and perhaps by longer cycles that have not been observed continuously. From Earth, Venus passes through phases like the Moon. At times it appears nearly full and small. At others it becomes a thin crescent, much larger in apparent size as it moves closer to Earth. Through each phase, the clouds continue reflecting sunlight, keeping the surface beyond ordinary sight. For early telescopic observers, those phases helped establish that Venus travels around the sun. But the cloud veil prevented the same observers from measuring the planet's rotation. Surface landmarks never appeared. Features seen in the atmosphere changed too quickly to serve as reliable markers for the solid world. For generations, the length of the Venusian day remained uncertain. The answer finally came through radar. Radio waves could penetrate the clouds, reflect from the ground, and return carrying information about the hidden terrain and its motion. The planet's rotation was revealed not by visible light, but by signals capable of passing through the veil. The clouds had hidden the surface without erasing it. They had only required a different way of seeing. As the descent continues, the reflective upper layers begin to close overhead. The brighter sunlight remains behind. Droplets become larger. The air becomes warmer, and the pressure begins to rise more noticeably. The pale planet seen from Earth is now above us. Below lies the deeper cloud, where falling acid begins to vanish into heat. Below the main cloud deck, the atmosphere changes character. The bright droplets become less numerous. Sunlight weakens. The air grows warmer and denser, and the last traces of suspended sulfuric acid begin to disappear. There is no clear moment when the clouds end. Instead, they thin. The haze becomes more transparent. Larger droplets evaporate. What remains is a deep atmosphere of carbon dioxide, carrying small amounts of nitrogen, sulfur compounds, water vapor, and other gases in quantities that can be difficult to measure with certainty. Above this level, the clouds dominate what the planet looks like. Below it, the gas itself becomes the environment. A descending probe would now be moving through air far heavier than anything found near Earth's surface. The pressure would continue rising, not in a sudden step, but steadily, as the weight of the atmosphere above accumulated. On Earth, most Finch changes in pressure happen over mountains, inside aircraft, or beneath water. On Venus, the atmosphere alone creates a descent into conditions that begin to resemble the pressure found deep below the sea. The comparison is useful, but not exact. Water and carbon dioxide behave differently. The Venusian atmosphere remains a gas through much of the descent, though near the surface its density becomes high enough to blur the ordinary distinction between air and fluid. Objects do not fall through it as they would through Earth's atmosphere. Parachutes encounter stronger drag. Heat moves differently. Sound would travel along unfamiliar paths through the dense carbon dioxide. Even the motion of a small machine would feel altered by the mass of gas pressing around it. The early Soviet Venera probes were built for this passage. Their descent capsules entered the upper atmosphere at high speed. Protected first by heat shields, then slowed by parachutes as the air thickened, the journey from space to the surface carried them through changing pressure, changing temperature, and changing chemistry in less than an hour. For the instruments inside, every minute brought a new Venus. The upper atmosphere was cold and thin. The cloud layers were acidic and bright. The lower atmosphere became darker, hotter, and increasingly compressed. Some probes released their parachutes before reaching the ground. This was not a failure. It was a deliberate choice. Once the air became dense enough, the capsule could fall more slowly without one. Remaining beneath a parachute would have prolonged the descent and exposed the equipment to rising heat for too long. The atmosphere itself provided resistance. The probe continued downward through carbon dioxide, thick enough to slow its fall, while the temperature around it climbed toward the limits of its design. These machines did not descend into a violent storm. Near the lower atmosphere, the winds were much weaker than those at the cloud tops yet. The density of the air meant that even a modest flow could carry force. The visual impression would have been different from the racing circulation above. There would be no bright cloud bands sweeping across the sky, no sharp horizon of blue air and open space. Instead, the surroundings would be filled with a heavy amber light, scattered through miles of atmosphere and filtered by the clouds overhead. The sun would be hidden. Its position might be guessed from a brighter region in the sky, but no clean disk would appear. Light would arrive diffusely, reflected and redirected so many times that shadows would soften. A landscape below could gradually emerge through the haze. At first, perhaps only a change in brightness, then darker shapes, then the broad outlines of plains, rocks, or slopes beneath the descending capsule. The sky above the surface of Venus is often imagined as deep orange. The exact appearance depends on local conditions, camera response, image processing, and the chemistry of the atmosphere. Some early surface images were reconstructed from data transmitted under extreme conditions, and their colors have been adjusted in different ways. Still, the broad picture remains. The light is muted, the atmosphere is thick, the surface is visible but never under a clear sky. As pressure rises, carbon dioxide becomes increasingly effective at trapping heat. Sunlight enters the atmosphere mainly as visible radiation. Much of it is reflected by the clouds, but some reaches deeper layers than the surface. The warmed ground then emits energy as infrared radiation. Carbon dioxide absorbs much of that outgoing infrared energy. The absorbed energy is passed through the atmosphere, emitted again, absorbed again, and redistributed. Because the atmosphere is so deep and dense, heat has difficulty escaping directly to space from the surface. The result is a powerful greenhouse effect. This phrase can sound as though the atmosphere is simply acting like a layer of glass. The real process is more complex. The atmosphere does not merely seal heat beneath the clouds. It exchanges radiation across many altitudes. It moves energy through convection. It transports heat through winds. It emits infrared radiation from levels high above the ground, where the atmosphere is finally cool and thin enough for energy to escape into space. The surface remains hot because it lies beneath an immense depth of infrared-absorbing gas. To reach space, the planet's thermal energy must work its way upward through that depth. This is why the high reflectivity of Venus does not make its surface cool. The clouds send much of the sunlight away, but the energy that remains is retained with great efficiency. Over time, the lower atmosphere and ground settle into a state far hotter than the surface of Mercury, even though Mercury lies closer to the Sun. Mercury has almost no atmosphere. Its daytime surface becomes intensely hot, but heat can radiate away directly. Its night side cools dramatically. Venus is different. Its atmosphere carries heat around the planet and holds it near the ground. The night side remains nearly as hot as the day side. The equator and higher latitudes differ far less in surface temperature than they would on a thinner air world. The lower atmosphere has removed much of the contrast that slow rotation might otherwise create. Venus takes longer to rotate once than Earth takes to orbit the Sun. A sunrise on the surface would unfold over a long interval. Daylight would persist for months by Earth's calendar. Night would last for a similar span. Yet the ground does not alternate between extreme heating and deep cooling. The atmosphere smooths those differences. It acts as a planetary reservoir, storing energy and moving it through a circulation that reaches from the surface to the upper clouds. Near the ground, convection becomes limited in unusual ways. On Earth, warm air often rises because it becomes less dense than the surrounding atmosphere. On Venus, the lower atmosphere is already extremely hot, and its temperature changes with altitude in a pattern shaped by pressure. A parcel of air moving upward expands and cools. A parcel sinking downward is compressed and warms. Across much of the lower atmosphere, temperature follows this pressure-driven pattern closely. The air can be stable against large vertical motions, even while smaller currents and local changes continue. The result is not a churning ocean of gas. It is a deep, compressed atmosphere whose lower levels can be relatively subdued compared with the fast-moving clouds overhead. Still, the surface and atmosphere are connected. Mountains disturb the flow, slopes redirect winds. Day-night heating differences, though reduced near the ground, may influence local circulation. Volcanic activity may release gases that enter the lower atmosphere and, over time, rise toward the clouds. The atmosphere also interacts chemically with surface rocks. At Venusian temperatures and pressures, minerals do not remain isolated from the surrounding gas. Reactions can occur between sulfur-bearing compounds in the atmosphere and materials in the crust. Some gases may be absorbed by the ground. Others may be released. The exact balance is difficult to determine because no long-lived station has measured these exchanges over months or years. Every surface lander has worked within a narrow window. The longest surviving Venera lander transmitted for a little more than 2 hours. That was enough to return images, measure the environment, and analyze parts of the surface. It was not enough to watch a full weather cycle, a seasonal change or a gradual chemical shift. The machines failed because the planet was not designed for them. Electronics overheated, pressure-tested seals and structures. The surrounding atmosphere delivered heat from every direction, leaving little opportunity for the lander to cool. On Earth, a machine can release waste heat into cooler air. On Venus, the air itself is hotter than many industrial ovens. A lander does not simply need to resist external heat. It must prevent that heat from flowing inward while also managing the heat produced by its own instruments. Insulation delays the process. Cooling systems can extend it. Eventually, the environment closes in. The images returned before that happened show a surface made of rock, flat slabs, broken fragments, rounded or angular forms lying beneath an orange sky. There are no visible pools of molten material around the landers. Although Venus is very hot, most common surface rocks remain solid at these temperatures. The landscape is not a global sea of lava. It is a rocky world under conditions severe enough to alter minerals, weaken machines, and erase any resemblance to the surface environment of Earth. The air near the ground is dominated by carbon dioxide, but its density gives it additional properties. Buoyancy would be stronger than expected for a gas. A balloon designed for the lower atmosphere would need to account for heat and pressure, but the surrounding carbon dioxide could support lifting gases in ways that differ from Earth. Even ordinary nitrogen and oxygen, if contained within a suitable structure at higher altitudes, would be buoyant in carbon dioxide. This has led to concepts for aerial exploration. The most favorable region lies much higher, within the cloud layers, where pressure and temperature are less extreme. But the deeper atmosphere also invites designs for robust descent vehicles, short-lived stations, and probes that could survive longer through high-temperature electronics. Each concept begins with the same lesson learned by the Venera missions. Venus cannot be treated as a slightly warmer Earth. Every system must be designed around the atmosphere, the pressure vessel, the thermal protection, the communications link, the parachute, the choice of materials, even the time available for science. The lower a machine travels, the more the planet dictates the terms. There is another effect of the dense air that is less visible. Refraction bends light. On Earth, refraction can lift the apparent position of the sun near the horizon or create mirages over hot ground. On Venus, the deep atmosphere bends light more strongly. A distant surface feature might appear displaced. The horizon could seem altered. Under some conditions, light from below the geometric horizon might curve through the atmosphere and reach an observer. The planet's appearance from the ground would therefore be shaped not only by haze and color, but by the optical weight of the air itself. Sound would also behave differently. The high density and carbon dioxide composition would change its speed and tone. A mechanical vibration from a lander, a gust moving across rock, or a distant impact would travel through a medium unlike the air around us. A human ear could not be present to hear it, but microphones and pressure sensors could translate that motion into signals. The lower atmosphere is not empty between the clouds and the ground. It is an environment with its own acoustics, optics, chemistry, and motion. It is also the region where the history of Venus becomes hardest to ignore. A planet does not acquire such an atmosphere without a long sequence of change. Carbon dioxide must come from somewhere. Water must be lost, stored, or transformed. Rocks must interact with gas. Volcanoes may renew parts of the atmosphere. Sunlight gradually reshapes molecules high above. Every layer carries a piece of that history. The clouds reveal active chemistry. The lower atmosphere reveals accumulated pressure. The surface temperature reveals the strength of the greenhouse state, and the scarcity of water points toward a planet that may once have followed a different path. Before reaching the ground, the descent pauses within this deep carbon dioxide sea. Above, the sulfuric acid clouds have disappeared from view. Below, the surface waits beneath air that has become nearly as dense as water in its effect on motion. The planet is no longer concealed by a veil, it is concealed by depth. At the end of the descent, the surface appears gradually. There is no sudden clearing beneath the clouds. The horizon gathers out of the haze. Shapes separate from one another. A darker patch becomes a rock. A sloping region becomes a plain. The ground arrives through the atmosphere, one layer of contrast at a time. For the first landers, this was the moment when Venus stopped being only a bright disk, a pressure reading, or a radar echo. It became a landscape. The Soviet Venera missions returned the first images from the surface during the 1970s. Later landers sent broader views in color. Their cameras revealed fields of broken rock beneath a sky filtered through the heavy atmosphere. Some stones appeared flat and layered, others were rough, angular, or partly buried in darker material. The landers had reached only a few locations, each representing a tiny area on a planet almost as large as Earth. Yet the images carried an unmistakable message. Venus had a solid surface shaped by geology. The ground was not hidden because it lacked structure. It was hidden because the atmosphere refused to reveal it in visible light. To see more, scientists turned to radar. Radio waves can pass through the clouds with far less interference than visible light. A spacecraft sends a signal toward the planet. The signal reaches the ground, reflects from ridges, plains, slopes, and rough surfaces, then returns to the spacecraft. The timing of the return helps determine distance. The strength and character of the echo reveals something about texture and orientation. By repeating this process across the planet, a radar instrument can build a map of terrain that human eyes could never see directly. The most complete radar portrait came from NASA's Magellan spacecraft. Magellan entered orbit around Venus in 1990. Over the following years, it mapped most of the planet's surface at a level of detail far beyond earlier surveys. Its images were not photographs. They were translations of radar echoes into patterns of brightness and shadow. A bright region might indicate a slope facing the spacecraft, a rough surface, or material that reflected radio waves strongly. A dark region might be smoother, tilted away, or less reflective. Reading those maps required care. Still, the hidden geology emerged. Venus is dominated by volcanic plains. Broad regions cover much of the planet, formed by lava flows that spread across older terrain and cooled into extensive surfaces. Some flows extend for hundreds of miles. Others overlap in layers, showing that eruptions occurred at different times. There are shield volcanoes with wide, shallow slopes. There are steep-sided volcanic domes. There are long channels that resemble the paths of very fluid lava. There are fields containing hundreds of small volcanic cones. gathered so closely that the landscape appears textured from orbit. The planet seems to have released heat through volcanism on an enormous scale. On Earth, much internal heat escapes through plate tectonics. Oceanic crust forms at spreading centers, moves across the planet, and descends again at subduction zones. Continents collide, plates break apart, volcanoes often trace the boundaries between them. Venus does not display the same global network. There are no clear equivalents of Earth's long mid-ocean ridges dividing major moving plates. There are no planet-spanning chains of subduction zones recycling crust in the familiar terrestrial pattern. This does not mean the surface is inactive. It means Venus releases and redistributes heat differently. Some regions appear stretched and fractured. Others seem compressed into belts of ridges. Large circular structures called coronae mark places where hot material may have risen from the mantle, pushing the crust upward before the center partly collapsed. Their rings can contain faults, fractures, and volcanic flows. A corona may span tens or hundreds of miles. Some are relatively simple. Others overlap with rifts, volcanoes, and deformed plains, creating landscapes that preserve several stages of geological change. There are also arachnoids. These structures resemble spiders in radar images, with a central circular feature and fractures radiating outward like legs. Their appearance likely reflects stresses in the crust related to rising magma, uplift, collapse, or combinations of these processes. The names are visual descriptions, not explanations. Each structure is a record of forces that acted beneath the ground. Among the most complicated terrains are the tesserae. Tessera regions are elevated and intensely deformed. Ridges and valleys cross one another in several directions, forming a pattern that can look like broken tiles. They appear older than many surrounding volcanic plains because younger lava often seems to cover or border them. Their origin remains uncertain. Some researchers interpret them as pieces of crust repeatedly compressed and stretched. Others have proposed that parts of the tesserae may have formed under conditions different from those of modern Venus, perhaps when the crust was cooler or when the planet contained more water. That possibility remains under investigation. No lander has yet returned a sample from a tessera region. Radar can show structure, elevation, and reflectivity, but it cannot provide the complete mineral history of the rocks. These highlands may preserve some of the oldest accessible material on Venus. If so, they could hold evidence from a period before the current surface environment became fully established. The planet's highest large region is Maxwell Montes. Its peaks rise several miles above the surrounding terrain, reaching elevations higher than Mount Everest rises above Earth's sea level. Because temperature decreases with altitude, the summit region is cooler than the lowlands, though it remains far beyond conditions familiar on Earth. Radar observations reveal unusually bright material at some high elevations. One explanation is that certain minerals become stable or condense there because of the lower temperature, coating the surface with a substance that reflects radar strongly. Several chemical candidates have been proposed, but the exact material has not been confirmed. Even on Venus, altitude creates a kind of climate. Not a climate of snow, forests, or moving water, but a change in chemical conditions across the sides of mountains. The low plains remain hotter. The high summits become cool enough for different surface reactions to occur. The atmosphere touches the land differently at different elevations. Across the broader planet, impact craters provide another clue to the age of the surface. Venus has far fewer visible craters than the Moon, Mercury, or many older planetary surfaces. Most of the craters that reaches appear relatively fresh. They are not heavily eroded, and few are partly buried beneath later geological layers. They are also distributed in a broadly random pattern. This led scientists to conclude that much of the visible surface is geologically young compared with the age of the planet itself, perhaps several 100 million years old on average. How that younger surface formed has been debated for decades. One early interpretation proposed a catastrophic global resurfacing event. In this picture, heat accumulated beneath a mostly rigid crust until widespread volcanic activity transformed much of the planet within a geologically short interval. Lava covered older terrain, erased many earlier impact craters, and created the broad plains seen today. Afterward, volcanic activity declined. A different interpretation suggests that resurfacing was more gradual. Under this view, Venus has experienced ongoing volcanic and tectonic activity across long periods, with different regions renewed at different times. Many smaller episodes, rather than one planet-wide catastrophe, could produce a surface with a limited crater population. The available evidence does not reduce neatly to one simple story. Some terrains appear older, some lava flows are clearly younger than neighboring features. Some structures may have remained active after the surrounding plains formed. The surface may record both broad episodes of change and persistent local activity. The question matters because it reaches into the interior. A planet nearly the size of Earth should still contain internal heat from its formation and from radioactive decay. That heat must move outward. Without Earth-like plate tectonics, Venus may lose it through mantle plumes, crustal deformation, widespread volcanism, or cycles of activity that operate over immense intervals. The clouds above contain gases that may also carry evidence from below. Sulfur dioxide is especially important. It can be removed or transformed in the upper atmosphere over time. If its abundance changes, one possible explanation is that volcanoes are adding new material. But atmospheric circulation and chemical reactions can also produce variations, making the signal difficult to interpret. Radar observations have offered more direct clues. Scientists comparing images acquired at different times have identified surface features that may have changed. In one widely discussed case, a volcanic vent near Mount Mons appeared to alter in shape between two Magellan observations separated by several months. The change was interpreted as possible evidence of volcanic activity during the spacecraft's mission. Another analysis found radar, bright regions that may represent relatively recent lava flows. These findings strengthen the case that Venus remains geologically active, though individual interpretations require continued testing. Radar images collected decades ago were not designed as a continuous volcanic monitoring system. Viewing angles, resolution, and processing can complicate comparisons. Future spacecraft will be able to return with instruments designed specifically to search for change. A fresh lava flow would alter radar reflectivity. A new vent might reshape part of a volcano. Changes in atmospheric gases could be compared with activity on the ground. Thermal observations might detect unusually warm regions through limited windows in the lower atmosphere. For the first time, it may become possible to watch Venus as an active planet rather than reconstructing its history from isolated clues. Mount Mons is one of the large volcanoes that will receive close attention. It rises several miles above the surrounding plains. Its broad slopes are marked by flows and fractures, and its summit contains complex volcanic features. Other major volcanoes include Sapus Mons, Ossa Mons, and Thea Mons. Their forms suggest repeated eruptions rather than single events. Lava spread down their flanks at different times, building broad structures layer by layer. Some volcanic domes on Venus have unusually steep sides and flat tops. They are sometimes called pancake domes. Their shape suggests lava thick enough to spread slowly while still forming a wide, rounded mass. Many are several miles across, far larger than most comparable domes on Earth. The atmosphere may influence how eruptions behave. Near the surface, pressure is so high that gases dissolved in magma may expand differently than they do under Earth's lower atmospheric pressure. Explosive activity could therefore be altered, though composition and local conditions would remain important. Lava would also cool beneath air, already heated to hundreds of degrees. The surrounding atmosphere would not stop solidification, but it would change the way heat leaves the flow. Any volcanic plume rising from the surface would enter dense carbon dioxide rather than thin terrestrial air. Ash, gas and particles would move through a medium that strongly resists motion. Some eruption products might remain low. Others could rise high enough to affect the atmosphere and, eventually, the cloud chemistry. The connection between volcanoes and clouds is one of the planet's deepest links. Sulfur released at the surface may travel upward. Sunlight transforms it. Acid droplets form. The clouds reflect the planet's brightness back toward Earth. A process beginning in dark volcanic rock may end as the luminous veil seen in the evening sky. The surface and clouds are not separate worlds. They are parts of one system. There is also the possibility of lightning, though the evidence remains uncertain. Some spacecraft have detected signals that could be consistent with electrical activity. Other measurements have not provided decisive confirmation. If lightning occurs, it may be connected to the clouds, volcanic plumes, or atmospheric processes, unlike those on Earth. Until dedicated instruments make repeated measurements, it remains an open question. Venus often offers evidence in this form. A signal appears. Another instrument sees less. A pattern suggests one explanation, while the atmosphere allows another. The planet is close enough to shine brightly, yet difficult enough that even basic questions can remain unsettled for decades. On the ground, the uncertainty feels distant. The rocks do not move visibly during the brief life of a lander. The air pushes against the hull. Heat passes through the insulation. The sky holds its amber light, but beneath that apparent calm, the interior continues to cool. Stress gathers in the crust. Magma may rise, gas may enter the atmosphere. A cross spans too long for any one mission to witness. The surface is renewed. The clouds hide the land, but they also carry traces of what the land is doing, and somewhere below them, Venus is still reshaping itself. The atmosphere of Venus did not begin in its present form. Like Earth, Mars, and the other rocky planets, Venus formed from material circling the young sun. Dust gathered into larger bodies. Collisions built a world. Heat from impacts, compression, and radioactive elements helped melt parts of the interior. Gases escaped from the rock. Water vapor, carbon dioxide, nitrogen, sulfur compounds, and other materials entered the early atmosphere through volcanic activity. Some gases may also have arrived, with water-rich objects striking the planet during the solar system's early history. At first, Venus may not have looked entirely unlike Earth. The two planets are close in size and formed at similar distances from the same star. Their bulk compositions are thought to share many features. Both developed rocky crusts, mantles, metallic cores, and atmospheres shaped by volcanic release. But Venus receives much more sunlight. That difference has influenced almost everything that followed. The young sun was dimmer than it is today, so early Venus may have experienced lower surface temperatures than the planet does now. Climate models have explored the possibility that liquid water could once have existed there, perhaps in shallow seas or long-lived surface reservoirs. The evidence remains incomplete. No spacecraft has returned samples from the oldest Venusian rocks. Much of the visible surface was reshaped long after the planet formed. The present atmosphere contains only traces of water, and the history of that water must be reconstructed from chemistry, climate models, and comparisons with other worlds. Still, the question is scientifically reasonable. Could Venus once have held oceans? The answer depends on how quickly the planet warmed, how much water it began with, how its clouds behaved, and how efficiently heat escaped to space. Water can influence climate in opposing ways. Water vapor is a greenhouse gas. It absorbs infrared radiation and helps retain heat. Clouds, however, can reflect sunlight and cool a planet, depending on their altitude, thickness, composition, and location. On a slowly rotating world, thick clouds may form over the region, receiving the strongest sunlight. Some models suggest that such clouds could reflect to keep its temperatures moderate for a time. Other models produce a warmer and shorter-lived period of surface water. The uncertainty is not a weakness in the science. It reflects the limited record available from a planet whose surface has been heavily altered and whose lower atmosphere is difficult to reach. At some point, Venus entered a climate state from which recovery became increasingly difficult. As the sun brightened over geological time, more water evaporated. Additional water vapor strengthened the greenhouse effect. The warmer atmosphere allowed still more evaporation. This created a feedback. If enough water entered the atmosphere, the upper layers became wetter than they had been before. Sunlight at high altitude then broke water molecules apart. Hydrogen, being light, could escape into space. Oxygen remained behind, where it could react with surface rocks, combine with other atmospheric species, or be removed through additional processes. Over long periods, the planet lost much of its accessible water. One clue survives in the ratio of deuterium to ordinary hydrogen. Deuterium is a heavier form of hydrogen. It has one proton and one neutron in its nucleus, while ordinary hydrogen has only one proton. Because lighter hydrogen escapes more easily, the water left behind becomes enriched in deuterium. Measurements of the Venusian atmosphere show a much higher deuterium to hydrogen ratio than that found in Earth's oceans. This strongly suggests that Venus once possessed more water than it does today. The ratio does not reveal a simple measurement of an ancient ocean. Scientists must account for the planet's starting composition, changing escape rates, volcanic release, and the length of time over which water was lost. Even so, the chemical pattern points toward depletion. The present dryness is not likely to represent the planet's original condition. As water disappeared, another process became important. On Earth, carbon dioxide is exchanged among the atmosphere, oceans, living systems, and rocks. Rainfall helps weather silicate minerals. Rivers carry dissolved material to the oceans. Carbon becomes locked into carbonate rocks and sediments. Plate tectonics later returns part of it through volcanism. This long geological cycle helps regulate Earth's climate across immense spans of time. Venus has no surface oceans today. There is no rain reaching the ground. There is no known biosphere drawing carbon from the air. And there is no confirmed system of plate tectonics operating like Earth's. Without a comparable carbon cycle, carbon dioxide released by volcanoes can remain in the atmosphere. The gas accumulates, the greenhouse effect strengthens. Heat alters the surface and the lower air. The atmosphere becomes both a cause and a record of the planet's changing state. This does not require a single dramatic moment. Venus may have crossed the threshold gradually. Each increase in temperature made the next increase easier. Each loss of water weakened the processes that might have removed carbon dioxide. Each change narrowed the range of climates the planet could support. Eventually, any remaining surface water would have evaporated. The oceans, if they existed, would have become atmosphere. Then sunlight would have separated their molecules, and space would have carried much of the hydrogen away. The term runaway greenhouse is often used for this process. It does not mean that temperature rises without limit. It means that the climate passes a point where additional warming causes enough evaporations to strengthen the greenhouse effect. faster than the planet can restore balance through ordinary surface cooling. The system moves toward a new state. For Venus, that state became a dry surface beneath a deep carbon dioxide atmosphere. Once established, it was difficult to reverse. Carbon dioxide became the dominant gas. Water became scarce. The clouds changed from any early water-based system into sulfuric acid layers seen now. The ground heated until chemical reactions between rock and atmosphere took place under conditions unlike those on Earth. The transformation may have required millions of years. It may have unfolded over much longer intervals. The exact timing remains uncertain because the planet has preserved so little accessible evidence from its earliest surface. The oldest terrains may contain clues. Tessera regions could hold minerals formed under cooler or wetter conditions. Certain rock types might indicate past interaction with liquid water. Granite-like compositions, if confirmed, would raise questions about how those rocks formed and whether water played a role. Radar observations can suggest differences in composition, but they cannot settle the matter alone. A future lander or sample return mission would need to reach these difficult highlands, survive the environment, and analyze the rocks directly. The atmosphere itself also preserves a partial history. Noble gases are especially valuable because they do not react easily with other materials. Their abundances and isotopic forms can provide information about atmospheric loss, volcanic release, and the building blocks from which the planet formed. Past missions measured some of these gases, but not with the precision needed to answer every question. Better measurements could help distinguish among competing histories. They might reveal whether Venus began with large amounts of water. They might clarify how much atmosphere was lost to space. They could show whether major volcanic release occurred early, gradually, or in repeated stages. The planet's present clouds are therefore connected to an older disappearance. Sulfuric acid droplets exist in an atmosphere that has lost most of its water. Carbon dioxide dominates because the processes that regulate it on Earth did not operate in the same way here. The heat below is the result of sunlight, atmospheric chemistry, geological activity, and time acting together. No single cause turned Venus into the world we see. Distance from the sun mattered, rotation mattered, cloud behavior mattered, the presence or absence of oceans mattered, the interior mattered. Chance may also have mattered through early impacts and the timing of major geological changes. Planetary histories are built from combinations, mutations. Two worlds can begin with similar materials and still separate. Earth retained surface oceans. Venus did not. Earth developed a climate in which carbon moves through air, water, rock, and life. Venus stored most of its carbon in the atmosphere. Earth's clouds contain liquid water and ice. Venusian clouds are made mainly of sulfuric acid. The contrast is sharp now, but it may have emerged through countless smaller differences over billions of years. This is part of what makes Venus so important. It is not merely an example of an extreme greenhouse climate. It is a record of planetary divergence. By studying it, scientists can ask which features of Earth's environment are stable and which depend on conditions that could have unfolded another way. They can test climate models under pressures and temperatures impossible to reproduce on a planetary scale in laboratories. They can examine how atmospheres escape, how volcanic gases accumulate, and how rocky planets respond as their stars change. These questions extend beyond the solar system. Thousands of planets have been found around other stars. Many are close to the size of Earth. Some orbit nearer to their stars and receive more energy, placing them in conditions that may resemble Venus more than our own planet. From far away, a Venus-like world could be mistaken for an Earth-like one. If only size and mass were known, its atmosphere would tell the deeper story. A thick carbon dioxide envelope, high clouds, scarce water, surface conditions hidden from direct view. Venus offers the nearest place where that story can be studied in detail. Its atmosphere is not a warning written for us. It is a physical outcome. A neighboring world followed the laws of radiation, chemistry, gravity, and geology into a climate state very different from Earth's. The clouds above it are the visible edge of that history. They formed after water declined, after carbon dioxide gathered, and after the lower atmosphere became hot enough to sustain the cycle that continues today. From the upper haze, the planet still reflects sunlight with remarkable brightness. Nothing in that brightness reveals how much was lost. The clouds conceal the surface. They also conceal an earlier Venus that may no longer exist anywhere except in isotopes, minerals, and the balance of gases still moving through the air. Within the clouds, there is a region where temperature and pressure become less severe. It lies roughly 30 to 40 miles above the surface, far above the heated plains and below the thinnest upper haze. Here, the pressure can approach values found near the surface of Earth. Temperatures can pass through a range familiar to terrestrial life. For this reason, the middle atmosphere of Venus has drawn attention from astrobiologists. The interest does not begin with evidence of organisms. It begins with a contrast. The surface is too hot for any known terrestrial biology. Higher in the clouds, heat alone is no longer the main barrier. The question shifts from temperature to chemistry, water, energy, and time. Those barriers remain formidable. The cloud droplets are made largely of concentrated sulfuric acid. Their acidity is far beyond that of nearly every natural environment inhabited by life on Earth. They contain very little available water, even though water molecules are present in small amounts. For biology, as we know it, the amount of water matters as much as its presence. A solution can contain water while holding it so tightly through chemical interactions that cells cannot use it. Scientists describe this condition with a measure called water activity. Earth organisms have been found in deserts, salt deposits, acidic mines, polar ice, deep rock, and heated ocean vents. Some survive conditions once thought incompatible with life. Yet even the most resilient known organisms require far more available water than measurements and models indicate within much of the Venusian cloud deck. This creates a difficult distinction. The cloud layers may have moderate temperatures. They do not necessarily offer a moderate habitat. A droplet floating there is not a tiny freshwater pond. It is a concentrated chemical environment capable of breaking apart many biological molecules. Proteins can lose their structure. Cell membranes can be damaged. Complex carbon compounds can react or decompose. Any organism living within such a droplet would need a chemistry unlike ordinary terrestrial cells, protective mechanisms far beyond those of known acid-loving microbes, or a local environment different from the cloud composition measured so far. Scientists have proposed ways such differences might exist. A droplet could contain dissolved material that partly reduces its acidity. Dust lifted from the surface might enter the clouds and provide minerals capable of reacting with sulfuric acid. Compounds containing ammonia could also change the chemical balance if they were present in sufficient amounts. These ideas remain hypotheses. They are attempts to explain unresolved atmospheric observations, not evidence that organisms are altering the clouds. The chemistry of Venus is complicated enough to produce surprises without biology. Sunlight breaks molecules apart in the upper atmosphere. Fragments recombine. Sulfur moves among several chemical forms: carbon monoxide, sulfur dioxide, water vapor, hydrogen chloride, and other trace gases vary with altitude and location. Particles move between layers before evaporating or forming again. A small error in understanding one reaction can produce a large difference in predictions elsewhere. The unknown ultraviolet absorber adds another uncertainty. Whatever causes the dark markings in ultraviolet images must take in sunlight or across particular wavelengths. Its identity has been debated for decades. Some proposed materials are entirely non-biological. Certain sulfur compounds can absorb ultraviolet light. Iron-bearing particles might contribute. Complex mixtures created by atmospheric chemistry may behave differently from pure substances measured in laboratories. Biological pigments have also been discussed because some terrestrial organisms absorb similar wavelengths, but a resemblance in color or absorption is not enough to establish a living source. Many unrelated materials interact with light in similar ways. The absorber may prove to be an unfamiliar chemical product of a planet whose atmosphere has never been sampled with the needed detail. The only way to know is to measure the particles directly. A probe would need to collect droplets at several altitudes, determine their composition, separate dissolved compounds from solid material, and examine how their properties change from the day side to the night side. It would need to distinguish material formed in the atmosphere from dust carried upward from the ground. It might also search for patterns that chemistry alone would have difficulty producing. Even then, caution would be necessary. Life detection is rarely a matter of finding one molecule. On Earth, oxygen can be associated with photosynthesis, yet oxygen can also form through non-living processes. Methane can be produced by microorganisms, geological reactions, or heat acting on organic material. A possible biosignature becomes persuasive only when its environment is understood and simpler explanations have been carefully tested. Venus offered a clear lesson in this difficulty when phosphine entered the discussion. Phosphine is a molecule made from phosphorus and hydrogen. On Earth, it can be associated with certain oxygen-poor biological environments, though it can also exist in industrial settings and under conditions very different from those at a rocky planet's cloud tops. In 2020, astronomers reported a spectral feature that they interpreted as phosphine in the atmosphere of Venus. The announcement received intense attention because known processes appeared unable to produce the proposed amount easily under Venusian conditions. But the measurement depended on identifying a faint signal within complicated telescope data. Other researchers re-examined the observations. Some found that data processing choices affected the strength of the feature. Some argued that sulfur dioxide, already common in the Venusian atmosphere, could account for part or all of the signal. Additional observations failed to detect phosphine at levels expected from the original interpretation. Other analyses continued to support the possibility that small or variable amounts might be present. The issue remains disputed. There is no accepted confirmation that phosphine exists in the Venusian clouds at a biologically meaningful abundance. And even if phosphine is eventually confirmed, its presence would not establish life. It would first establish a chemical question. Scientists would need to determine where the gas forms, how long it survives, how it is transported, and whether volcanic, mineral, photochemical, or other processes could produce it. A molecule can be interesting without being an organism. The debate changed Venus science in another way. It showed how little is known about trace chemistry in the clouds. The major ingredients have been measured for decades. Carbon dioxide dominates the atmosphere. Nitrogen forms most of the remainder. Sulfuric acid makes the clouds. Yet rare compounds can reveal processes hidden within those broad categories. A gas present in only a tiny proportion may trace volcanic release, reactions on particle surfaces, movement between atmospheric layers, or chemistry not yet reproduced in laboratories. Venus is close to Earth, but its clouds have not been examined with modern instruments from within. Since the Soviet Vega balloons crossed them in 1985. Those balloons measured physical conditions and motion. They were not equipped to perform the full range of chemical and microscopic analysis now imagined. A future balloon could remain in the temperate region for days or weeks. Carried by super-rotating winds, it could circle much of the planet. It could sample different local times and latitudes while rising and falling through selected layers. Its instruments might count particles. They could measure droplet acidity and water content. They could identify metals, salts, sulfur compounds, and organic molecules. They might search for repeating structures within droplets, though finding such forms would still require careful interpretation. A sphere, filament, or membrane-like shape is not automatically biological. Mineral crystals and chemical droplets can organize themselves into intricate patterns. The strongest investigation would combine several kinds of evidence: chemical disequilibrium, complex molecules, unusual isotope ratios, structures that repeat in ways expected from growth or division, a surrounding environment able to sustain the processes being proposed. Each result would need to agree with the others. The clouds would also need to provide a complete life cycle. A microbe suspended in a droplet cannot remain at one altitude forever. Droplets collide and settle. Winds carry them upward or downward. As they descend, heat causes them to evaporate. Any long-lived population would require a way to survive these movements. One proposed cycle begins with active cells inside cloud droplets. As the droplets fall and lose water, the cells would enter a dormant state. Tiny dried particles might remain suspended in a lower haze, later carried upward by atmospheric motion. Once returned to cooler cloud layers, they could become enclosed in new droplets and become active again. It is an elegant possibility. No such cycle has been observed. Its stages must overcome the acidity, dryness, radiation, scarcity of nutrients, and uncertain vertical circulation of the real atmosphere on Earth. Airborne microbes can travel through clouds, but the clouds are not their only environment. They generally originate from oceans, soil, plants, or other surfaces, and eventually return to them. Venus offers no known refuge below. If cloud life exists there now, it may have needed to remain aloft for a very long time. Perhaps to surface conditions became uninhabitable. That would make the atmosphere not merely a temporary habitat, but the last surviving layer of an older biosphere. This idea depends on Venus once having habitable surface conditions, which remains uncertain. Some climate histories allow long periods with liquid water. Others suggest the young planet may have been too warm for oceans to condense and persist. Until ancient rocks are analyzed, an atmospheric history is better constrained. Both the origin and survival of hypothetical cloud life remain open questions built upon other open questions. The scientific value does not depend on the answer being life. A sterile cloud deck would still teach us where habitability ends. It would show that familiar pressure and temperature cannot overcome extreme acidity or insufficient water. It would help define which environmental limits come from the details of Earth biology and which may apply more broadly to carbon-based organisms. A chemically active but lifeless atmosphere would also explain how false biosignatures can arise on distant planets. Future telescopes may examine rocky worlds around other stars and detect clouds, gases, or atmospheric imbalances without ever seeing their surfaces. Venus provides a nearby test. Here, instruments can eventually enter the atmosphere and compare remote signals with direct measurements. Scientists can learn which spectral features are trustworthy, which are ambiguous, and which require context that a distant telescope cannot provide. The planet may therefore help in the search for life, even if life is found within its clouds. It can teach us how not to mistake chemistry for biology. For now, the droplets continue their cycle. They form where temperatures allow sulfuric acid to condense. They travel around the planet in the high winds. They absorb and scatter sunlight. They descend toward warmer air and vanish. Within them, there are unsolved reactions and unidentified materials. There is no confirmed organism. There is no confirmed biological gas. There is only an environment close enough to investigate, difficult enough to challenge every assumption, and rich enough in chemistry that simple answers rarely survive for long. The clouds do not promise life, they invite a careful measurement. To understand the clouds of Venus, scientists must learn to observe a planet that resists every visible light reveals the cloud tops, but not the ground. Radar reveals the ground, but not the full chemistry of the clouds. Orbiters can watch global patterns, yet they remain far above the droplets they are trying to explain. Landers can measure the lower atmosphere directly, but heat and pressure limit how long they survive. Each method reaches one part of the planet and leaves another part hidden. The first spacecraft to approach Venus treated the atmosphere as an obstacle. Later missions began to recognize that the atmosphere was the destination. A descending probe can measure temperature and pressure continuously as it falls. It can record how winds change with altitude, identify gases, and count cloud particles. It can sample a vertical column of atmosphere that no telescope can reproduce from afar. But the descent is brief. The probe moves through each layer only once. A chemical feature detected at one altitude may be local, temporary, or influenced by the time of day. A wind measured during one passage may not represent the circulation elsewhere on the planet. To understand a moving atmosphere, scientists need motion of their own. Balloons offer one solution. Within the middle clouds, a balloon could float at an altitude where pressure and temperature are less destructive than they are near the surface. It would travel with the winds, becoming a patient observer carried around the planet. The Soviet Vega balloons demonstrated that this was possible. Their journeys lasted less than 2 Earth days, but they crossed large distances and revealed turbulence, vertical motion, and changes in the surrounding air. A longer-lived balloon could do much more. It could follow the transition from day to night. It could measure how cloud chemistry changes as sunlight disappears. It could compare equatorial regions with higher latitudes. By adjusting its buoyancy, it might rise and descend through selected layers, sampling the upper, middle, and lower cloud deck without falling all the way to the ground. In this way, one instrument could build a 3-dimensional record. Temperature would be measured beside chemistry. Wind would be measured beside particle size. Ultraviolet absorption could be compared with the actual substances inside the droplets. A dark marking seen from orbit could be entered directly. The unknown absorber would no longer be only a pattern in an image. It would become a sample passing through an instrument. The difficulty lies in survival. Sulfuric acid attacks exposed materials. Cloud droplets can enter openings, coat sensors, and alter optical surfaces. A balloon envelope must remain flexible while resisting corrosion. Solar panels, antennas, valves, and instruments must function after repeated contact with acid aerosols. The environment is milder than the surface, but it is not forgiving. Every exposed component must be chosen with care. Orbiters provide the broader view. From above, radar instruments can map terrain beneath the clouds. Spectrometers can examine gases at different altitudes. Cameras can track ultraviolet markings and follow cloud motion across the entire planet. Repeated observations are especially important. A single image shows structure, a sequence shows change. By returning to the same region, an orbiter can search for new lava flows, shifting cloud patterns, changes in sulfur dioxide, or thermal signals associated with geological activity. The atmosphere and surface can then be studied together. A change near a volcano might be followed by a change in the clouds. A large atmospheric wave could be compared with the mountain range below it. A region of unusual chemistry might be tracked as winds carry it around the planet. The hidden layers begin to connect. Radar also allows scientists to examine the surface with greater precision than earlier maps provided. Improved resolution can reveal small faults, narrow lava channels, landslides, and subtle changes in volcanic vents. Repeated radar passes can measure deformation, showing whether the ground has risen or fallen between observations. On Earth, such movement can reveal magma gathering beneath a volcano. On Venus, the same principle could identify active geological regions without placing an instrument on the surface. Yet, orbiters cannot answer every question. Radar brightness does not uniquely identify a mineral. An atmospheric spectrum can show that a molecule absorbs light, but not always where it formed. A thermal anomaly may suggest fresh lava, though surface composition and atmospheric effects can complicate the signal. At some point, the planet must be touched. Future descent probes may carry instruments able to measure noble gases and isotopes with far greater precision than earlier missions. These measurements could help reconstruct the origin and loss of the atmosphere, the abundance of argon, neon, xenon, and their isotopes would offer clues about the material from which Venus formed. Hydrogen isotopes would sharpen estimates of water loss. Ratios within carbon, nitrogen, and sulfur could reveal how gases moved between the interior, atmosphere, and space. A probe descending for only an hour can still recover evidence spanning billions of years. The challenge is deciding where to sample. The atmosphere changes with altitude, so a single measurement near the surface cannot describe the cloud deck. A sample taken high above the clouds cannot explain reactions occurring below. An ideal descent would analyze gases repeatedly. It would measure the same molecule at several levels, watching its abundance rise or fall. It would collect droplets in the upper clouds, then repeat the process deeper down. It would determine whether large particles differ chemically from small ones. It would observe when sulfuric acid begins to evaporate and what remains after the droplets disappear. The descent path itself would become a chemical profile of the planet. Near the surface, instruments would face the most severe conditions. Pressure vessels must resist the weight of the atmosphere. Electronics must operate at temperatures that would disable ordinary spacecraft systems. Cameras must look through thick windows without those windows clouding, deforming, or reacting with the environment. Traditional cooling can extend a mission for a limited time, but a longer-lived lander may require electronics designed to work while hot. This changes the philosophy of exploration. Instead of protecting ordinary electronics from Venus, engineers can build systems that accept Venusian temperatures as normal. High-temperature semiconductors, durable sensors, and simple mechanical components could allow instruments to function for much longer than previous landers. A station surviving days rather than hours could watch the lower atmosphere change. It could record pressure waves. It could measure winds across the slow transition from daylight to night. It could listen for seismic motion in the ground or disturbances passing through the dense air. Even a simple weather station would transform our understanding if it remained active long enough. The surface day on Venus is longer than many spacecraft missions. A lander operating for only a few hours sees almost no change in solar position. It cannot observe a full daily cycle or determine how local winds respond over time. Longevity would turn a brief encounter into a record. The most scientifically valuable rocks may be found in the Tessera highlands. Reaching them is difficult. Elevated terrain can be steep and rough. Landing sites must be chosen with limited direct imaging. Radar provides maps, but small hazards may remain unresolved. A probe sent there would need to survive descent, land safely, and analyze material that may preserve an earlier period of Venusian history. The reward could be considerable. If the rocks contain minerals that formed in the presence of liquid water, they would strengthen the case for an earlier habitable climate. If they resemble volcanic crust formed without water, they would point toward a different history. Either result would narrow the possibilities. Some mission concepts look beyond stationary landers. Small aircraft could fly within the clouds. Gliders might use changes in wind and altitude to travel without continuous propulsion. Multiple balloons could separate and sample different regions at the same time. Tiny probes might be released from a larger carrier, building a network across the atmosphere. A single measurement would become a pattern. One balloon could observe the day side while another crossed into night. A descent probe could pass beneath them while an orbiter watched from above. For the first time, several layers could be studied together. This coordination is important because Venus does not divide itself into isolated questions. Cloud chemistry depends on circulation. Circulation responds to sunlight and terrain. Atmospheric gases may come from volcanoes. Surface minerals react with the lower air. Hydrogen escapes from the upper atmosphere. Every region influences another across different timescales. An orbiter, balloon, descent probe, and lander would not be repeating the same work. They would be completing one another. There is also value in observing Venus from Earth. Powerful telescopes can monitor the planet for years, long after a spacecraft mission ends. Radar observations can track surface properties. Spectroscopy can search for changes in trace gases. Amateur observers can record broad cloud patterns in wavelengths accessible from the ground. The planet's brightness, once an obstacle to seeing beneath the clouds, makes long-term monitoring possible. No single observatory must watch continuously. Measurements gathered across many seasons can reveal whether the atmosphere follows cycles that shorter missions might miss. The super-rotating winds circle Venus in days. The solid planet rotates in months. Volcanic activity may vary over years or centuries. Atmospheric loss unfolds across geological time. Studying Venus requires instruments that can hold these different clocks together. The next clear answer may come from a droplet collected inside the clouds. It may come from a radar image showing that a volcanic vent has changed. It may come from an isotope measured during a descent, or it may come from an old dataset examined with a method that did not exist when the signal was first recorded. Exploration is not always a straight descent towards certainty. Sometimes it is a widening network of measurements, each one reducing the space in which an explanation can hide. Venus has concealed its surface for the entire history of human observation. It has concealed the chemistry of its clouds for nearly as long as spacecraft have visited it. But concealment is not the same as inaccessibility. Radio waves pass through. Balloons can float within. Probers can fall between the layers. Landers can endure for a while, and with each return, the bright veil becomes less like a barrier and more like a place that can finally be entered. From Earth, Venus remains familiar. It appears in the west after sunset, or in the east before sunrise, bright enough to cast a faint shadow under the right conditions. Its position changes from week to week as Earth and Venus move around the Sun, but the planet itself still looks much as it did to observers thousands of years ago. A pale point, a steady light, a world hidden inside its own atmosphere. What has changed is not the view from the ground. It is the depth of the questions behind it. The clouds once seemed like a blank covering. They are now understood as an active chemical system built from sulfuric acid, droplets, and shaped by sunlight, circulation, gravity, and heat from below. The smooth globe once suggested calm. It now reveals winds that move around the planet in only a few Earth days, polar vortices that twist and reorganize, and atmospheric waves that may begin above, mountains no eye can see. The bright veil once prevented knowledge of the surface. It now provides clues about the rocks, gases, and volcanic processes beneath it. Venus has not become simple through exploration. It has become more complete. The layers no longer stand apart. The upper atmosphere loses particles and atoms to space. The cloud deck transforms sulfur compounds under sunlight. The lower atmosphere stores heat and presses against the ground. The surface releases material, reshapes itself, and reacts with the air above it. The interior supplies energy across spans far longer than any mission can observe. Every part belongs to the same planetary system. A molecule of sulfur dioxide released near the ground may rise over time, enter a region of stronger sunlight, and become part of a sulfuric acid droplet. That droplet may travel around the planet, descend into warmer air, evaporate, and return its material to the gas. A hydrogen atom once contained in water may rise high enough to escape Venus entirely. A wave generated by wind crossing a mountain may climb through tens of miles of atmosphere before leaving a pattern visible from orbit. The planet is connected vertically as well as horizontally. Its clouds are not only a ceiling, they are a moving boundary between the heated world below and space above. The scientific questions that remain are precise. How much water did Venus begin with? Did oceans ever remain on the surface? When did the present greenhouse state become established? How often do volcanoes erupt now? What creates the unidentified ultraviolet markings? How does the atmosphere maintain its rapid superrotation? Which minerals survive in the highlands? How do sulfur compounds move between rock, air, and cloud? There may be answers in gas samples, radar maps, droplets, and old rocks. Some will come from short descents. Others will require years of observation. A few may remain uncertain even after new missions return. That uncertainty is not a gap to be filled with imagination. It is part of the planet as science currently knows it. Venus teaches patience because nearly every measurement arrives through interference. The surface is seen through radar echoes. The lower atmosphere is known from probes that survived only briefly. The cloud chemistry is reconstructed from remote spectra and limited direct sampling. Possible volcanic change must be separated from differences in viewing geometry. Trace gases must be distinguished from overlapping signals and instrumental effects. The planet rarely offers an answer without also revealing the limits of the method used to obtain it. This makes Venus a valuable neighbor. It is close enough that spacecraft can reach it without crossing the outer solar system. It is large enough to retain a deep atmosphere. It formed from materials related to those that built Earth. Yet it followed a different climatic and geological path. The comparison does not reduce either planet to a lesson about the other. Earth is not simply Venus before disaster. Venus is not a failed version of Earth. They are separate worlds shaped by different distances, rotations, atmospheric histories, water inventories, interior processes, and sequences of change. Their similarities make the differences measurable. Their differences reveal how many possible outcomes exist for rocky planets. This matters as astronomers study worlds around other stars. A distant planet may have nearly Earth's radius. It may orbit within a region where temperatures appear suitable for liquid water. It may possess clouds that reflect large amounts of starlight. Without information about its atmosphere, those facts may say little about conditions on the ground. Venus demonstrates how a rocky planet can hide its true state beneath brightness. A reflective world can be intensely hot. A cloud-covered world can be almost dry. A planet with familiar size and gravity can have an environment unlike any place on Earth. Future observatories may identify many worlds that belong more closely to the Venusian family than to the terrestrial one. Understanding our neighboring planet will help scientists recognize them. The clouds of Venus are therefore local and distant at the same time. They belong to one world beside Earth. They also provide a model for interpreting planets that may never be visited. Every improved measurement here strengthens the questions we can ask elsewhere. For now, the direct experience of Venus remains mechanical. Metal capsules fall through the atmosphere. Radar signals cross the clouds. Spectrometers divide light into narrow bands. Balloons move with the wind. No human has stood beneath the Venusian sky. No person has watched the dim sunlight spread across plains or seen the horizon bend through the heavy air. The planet is known through instruments that extend perception into places the body cannot enter. There is something fitting in that distance. Venus is one of the nearest worlds, yet physical closeness has never meant easy access. It has required new materials, new methods, and repeated attempts. Several early spacecraft failed before returning useful data. Later probes lasted minutes where engineers hoped for longer. Each success depended on accepting the environment rather than imagining it could be made familiar. The clouds demanded ultraviolet cameras, the surface demanded radar, the pressure demanded sealed vessels, the heat demanded insulation and new electronics. The chemistry demanded caution. The planet established the terms of observation. Human exploration advanced by learning to meet them. When the next probes descend, they will enter an atmosphere already partly known. They will pass through regions measured by earlier spacecraft and continue questions that began decades before their launch. The instruments will be newer, but the passage will remain the same. First the thin upper air, then the bright haze, then the acid clouds, then warmer layers where droplets, then the deep carbon dioxide atmosphere, then the ground. Along that route, every reading will belong to a vertical story, billions of years in the making. Temperature profile will describe more than weather. A noble gas ratio will carry information from planetary formation. A cloud particle may connect sunlight to volcanic chemistry. A rock may preserve a period before the modern atmosphere took shape. Even a wind measurement may help explain how the entire atmosphere moves faster than the planet beneath it. The descent will not reveal everything. No single journey can. But it may connect pieces that have remained separate for too long. From the outside, Venus will continue to shine. Its clouds will keep reflecting sunlight across the space between the planets. Some of that light will reach Earth and enter the eye of someone looking toward the horizon without a telescope. They may not think of sulfur cycles, carbon dioxide pressure, radar maps, or atmospheric escape. They may only notice that one point is brighter than the others. That simple view is still accurate. Venus is bright because of its clouds. The deeper truth is that those clouds are not a feature placed over the planet. They are the visible expression of the planet's history. They contain the consequences of lost water, persistent volcanism, solar radiation, atmospheric circulation, and a greenhouse climate sustained over immense time. They hide the surface while linking it to space. They make Venus easy to see and difficult to know. And they remain in motion long after the planet has set below the horizon. The clouds keep circling,